In this video and for other videos, we will either calculate or derive the chemical potential of a helium gas in a mixture under various conditions: constant TV, constant TP, and constant HP. Now let's look at the simplest case. When temperature and pressure are held constant, the chemical potential of a pure species is simply its molar Gibbs energy, and this is a relative quantity. We can set different zero references. There are two ways to define this standard molar Gibbs energy. One is this: the standard molar Gibbs energy is equal to the standard Gibbs energy of formation. Another way is this: it's the standard enthalpy of formation minus temperature times the standard molar entropy. Using this equation is more convenient because the second expression, well, involves the value of the standard molar entropy. We need to look it up. So let's stick to the first expression to calculate the chemical potential of the helium gas in a mixture first, and later I'll show you these two expressions will result in the same expression for chemical potential. The second expression is just a little bit more tedious. Now let's use this equation. Let's assume the standard molar Gibbs energy is equal to the standard Gibbs energy of formation, and we know these two are equal to 0 for a pure helium in the standard state at room temperature, just by definition. Now we have this equation from UPAC. Mu is delta G over delta N. Alright, and then we're going to use the finite change of the Gibbs energy divided by the finite change of the normal mole to estimate the numerical value of the chemical potential of a helium gas in a mixture. Alright, let's focus on this. To perform the numerical calculation, we need to know two things. We have learned those before. Number one, Gibbs energy is additive, so delta G is the sum of the Gibbs energy changes of all components in the system. Number two, the molar Gibbs energy of an ideal gas is simply the standard molar Gibbs energy of this species plus a correction, RT times the natural logarithm of the partial pressure of this species divided by 1 bar. Now let's quickly review the various definitions of chemical potential. We introduced 12 of them, but many are less commonly used. We will only verify these three definitions are equivalent to each other. We will see the chemical potential is equal to delta G over delta N under constant TP condition. Also, it's delta A over delta N on a constant TV condition, or negative T times delta S over delta N on a constant HP condition. We'll show you all three expressions will end up to be this. The chemical potential of a helium is just the standard chemical potential plus RT times the natural logarithm of the partial pressure of this gas over P naught. Over here, I'm just showing you the wheel of thermodynamics, U, H, G, and A. Again, U plus PV, you get H, H minus TS, you get G, and G minus PV, you get A plus TS, you get U. Mu is the central piece of this wheel of thermodynamics. Now let's look at the first numerical example. Let's look at the simplest condition: constant temperature and pressure. So under the constant temperature and pressure condition, mu is delta G over delta N. We'll just calculate the finite change of G and N. So first let's look at a simple system. There's a 1 bar gas mixture. Inside we have 0.4 moles of helium, 0.6 moles of argon. We can get the partial pressures of the two gases, and then we add a very small amount of helium into the system to get a finite change of G. and we have this finite change of the amount of helium. And then we do the division, we get the chemical potential. After the addition, we need to calculate the new partial pressures for helium and argon. So the partial pressure of helium is now a little bit more than 0.4. The pressure of argon is a bit less than 0.6, but the sum is still 1 bar. Again, we are holding the total pressure of the system constant. Now we need to compute the finite change of the Gibbs energy. It has 3 components. So first, we added this amount of helium, so we need to compute the Gibbs energy of the added helium. And then we need to calculate the change of the Gibbs energy of the pre-existing helium and also the Gibbs energy change of the pre-existing argon. So first, the added helium. Well, what's the Gibbs energy of the added helium? It's the number of moles here times RT times the natural logarithm of the pressure of this added helium, 0.4006, divided by P naught. So it's simply this. Again, we're assuming the standard molar Gibbs energy is the same as the standard Gibbs energy of formation for helium, which is just 0 at room temperature. Therefore, this is the absolute value of the Gibbs energy of this small amount of added helium. Now let's look at the change of Gibbs energy for helium and the change of the Gibbs energy for argon. It's here and here. Look at this. We have 0.4 mole of pre-existing helium. This is the pressure change. We have 0.6 moles of argon in the system, and this is the pressure change from 0.6 to 0.4 or 0.5994. So again, there are 3 components: the added helium, the change of the pre-existing helium, the change of the pre-existing argon. We sum it up, we get the finite change of G divided by the finite change of N helium. We get negative 2.2696 kilojoule per mole. This is supposed to be the numerical value of the chemical potential of this helium in the mixture. Now we use the analytical expression of the chemical potential. It's this: mu naught plus RT times the natural logarithm of the partial pressure of helium over P naught. We get negative 2.27144. If you compare these 2 numbers, well, they differ by a very, very small percentage. And we can even do better by changing this 0.001 to a smaller amount. So here's our second example problem. We will add only 0.00001 mole of helium in the system, 10 to the power of negative 5. And also, we follow the same steps. We calculate the new pressures of helium and argon. We add up the 3 components of the changes in Gibbs energy. We do delta G over delta N. We get this negative 2.27143. Compared to this analytical expression, well, they differ by, I think, less than 0.001%. Again, if we do this numerical calculations by adding a smaller amount of helium, we get more accurate numerical result. So both numerical calculations agree with this analytical expression. And then we will prove this by adding a infinitesimal amount of helium. So we're going to use dn here in this same mixture. We'll get this analytical expression in the next video.